Okay, today we're going to see an introduction to our class Vehicle Safety and Crash Reconstruction. And what we're going to do is some tutorials that would allow you to um, begin learning Working Model 2D. Working Model 2D is a very useful software for the subject because it would allow us to do computer simulations in 2 dimensions, and would allow us to understand the principles of dynamics and the principles of conservation of momentum, which are very important to what we're doing here. So let's get ourselves started. I'm going to disappear from here, and then we're going to go over here to Working Model 2D, which you can see is we see the software over here. Um, this is just a place where you can draw things, objects, and put situations in here as you want. One thing that I like is to have the see where it says workspace. I like the rulers and also the grid lines. It sort of gives us a little bit more of a reference point. You can take them off if you want, but also I like to have the, see, let me move this a little bit here, the XY axis in here, you see in there, the 0, 0. So everything you draw here is in relationship to an axis. Do you see in there? See, it's coming up. So the reason that it's important is because um, you can reference things with respect to the axis. See, Working Model will allow you to place it anywhere in there, but it's nice to have the reference, um, on a Cartesian plane, because you want to enter exact dimensions. Right now, for what we're doing today, it's not as important, but it will become very important if you have if you're going to investigate a crash of vehicles, you need to map the scene, and the scene needs to be precise, and also the vehicles too. So in here, I am going to show you some very basic principles and some um, some um, some features of this program. For example, this on the left hand side, let me just explain to you here. There is a way to do the shapes. Here there is a menu which is not in words but in pictures of different shapes that you can use to draw things here. On this one, of course, we draw it with shapes like this, and or like this. But on this one, you can draw different objects of different shapes like that. So you create like, okay. Or this other one creates to create like camps, for example. This is very easy to do that. In all of this, one thing that you should remember is that what you are seeing on the screen is actually not a drawing. It's a rigid body with properties. Let me show you what I'm saying. If you double click on here, you see what it's in here? So that you can see that this program is totally different than a CAD package, for example. In a CAD package, you make a drawing, and then it has lines and dimensions, things like that. But this one instead has rigid body properties. And so from the very beginning, it's very important that you understand what we're doing here. See, if I change the location of this, watch how this is gonna change. If I put it on the center of, do you see how it goes to 0, 0? I could center it exactly where I want, you know? It's at the 0, 0 axis, the center of mass of the, that's the other thing. This has a center of mass. Like I say, it's a rigid body. It's a slab with a rigid body. And this indicates the rotation in radians. How much would the body rotate if I put a 1 in here? Let's see, those good brains. How many degrees is 1 radian? Don't remember? Pi divided by 3, right? No, pi divided, yeah. So 1 radian is 100, what am I saying? 180 degrees divided by pi. That would be the number of degrees for 1 radian, which is 51 something, right? See, if I put 1 in here, watch what the body does. See? So you have the ability not only to position the body where you want, but also to make it rotate any way you want. If you put it at 0, it's going to go back. And if I do a -1, it's going to turn the other way. You see what I mean? Also, in here, I could give it an initial velocity in the x direction, like for example 10. And with this, if I click on run here, what am I saying? We're saying start at time 0, give this body, we are doing in meters per second, 10 meters per second speed to the right, and see what happens. So what would the expect it will do? Think about this. Maybe it will fall, but also is going to move to the right. So it's going to have a combined motion in here because gravity is acting. So let's see if this is true. See? Which is exactly what what you suggested here. So let's move it here so we can see it. See there? Yeah. If the initial velocity in the x direction will not be there, then obviously if this is 0, this will fall down, straight down. Yeah? See? Do you see what I'm trying to say from the get-go? This is not a cat pocket. It has dynamics to it. And the reason it falls because of gravity. And it's gotta fall with the acceleration of gravity. Now, if we take gravity away from this, what will happen? Think about this. I am doing this deliberately to make you think that depending on the situation or what you want to simulate, you will accommodate the reality to what it is. So if you go in here in the world, you see there's this gravity. Vertical gravity is how we live. You know, this is the planetary gravity would be in a plane. But if you see no gravity, what will happen if I click on run? Nothing. Yeah? This is equivalent to having a top view. Yeah? So that's the equivalent of this. So if you give in here velocity of 10, we don't have to worry about gravity anymore, but rather it will move to the right. You see? Reset, move to the right. Yeah? So we can adjust to whatever situation that we want. But what is important to us at this point is, let me put the body back at 0 and with initial velocity 0. But you see, we could also give it a rotational velocity. If I put the 1 radian per second in here, what should we see right now? The body, you see what it does? So what I'm trying to do is this program empower us to tell the computer, look, this is the situation here. In the case of a of a vehicle collision, we need to build the scene, and then we need to build the cars, and then we need to build the conditions upon which we know the accident likely occurred, and then test many simulations to make sure that the evidence and the reality and the simulation match together. If you achieve that, it's going to be very difficult to argue that it happened some other way. And that's what I am trying to tell you, that in this university we have basically perfected this technique for many applications, and we're doing this now for vehicle dynamics and accident reconstruction here. So in here you have, you see the mass. Let's look at every single thing in here, because you're going to be faced with all this. See here, you can build the bodies out of different materials. If you pick a steel, it will get the properties of steel. Let's just, for the sake of example, let's do that. You see in here you have the modulus of, you'll have the static friction, the mass of this. Of course, you could change the mass. The shape could be different, but the mass could be also different. You have the density, 8 kilograms meter. If you change it to ice, which is water, basically, you see the density 0.9, which is of ice. Yeah? If you change it to rubber, see, 0.5. You get to, we'll leave it at the standard in here. And that way we can manipulate and tell the computer this is made of any material with the properties that we know it has. In the case of vehicles have a stiffness, and that's what we need to do. And also, one thing I want you to think for a moment is the static friction would be how much it takes for a body to overcome the force of friction, right? Um, but also, you know that there's the kinematic coefficient of friction, right? Which is which is less than the static one, and it's when the body is already moving. So that's the. And then you have uh, the this number that is the elastic here. We are going to concentrate on that, because this number is the so-called is coefficient of restitution, which tells us whether the collision is elastic or is plastic collision. Okay, so these are the things that I can tell you based on our experience that we have in here to be able to give this subject a base, solid scientific base. And we have this, it has also the moment, this is the moment of inertia, see? So now that hopefully I have convinced you that this is not a CAD program, everything you see on the screen has properties, has dynamic properties. So it is important to me at this point to be able to explore the properties and in particularly in this case understand what the coefficient of restitution is, because that's crucial to accident reconstruction and vehicle safety, because it is a measure of how elastic or plastic a vehicle is. Now, in the past, when you look at the vehicles that were built, let's say in the 60s, I have an old Impala 1969 Chevrolet in some storage there because it's a classic car. This car, at the time, seat belts were a luxury for those cars. But the seat belt is about close to 5 inches wide, okay? And doesn't have one like we normally do now. It has two of them. So you have to do a lap seat belt and you have a shoulder seat belt also. Um, at the time, there was no flexibility. In other words, once you are there, you are there. You don't move. So you better put a little bit of slack on the seat belt yourself, because otherwise you are fixed. Right? I can see why they would do that at the time, because restraining systems were not developed very well. Airbags did not exist, and the cars were really stiff. You get in an accident with one of these cars, and you're gonna hit the steering wheel very quickly and cause a lot of damage to the other car as well as to yours. Why? Because the forces that develop when the cars are stiff are much higher than the forces that develop when they are squishy, if I can use that word, because it is important to use simple words to understand things. But the car cannot be totally squishy either, because otherwise it will get to you. So there's gotta be some restitution in there, some stiffness, that the car gets deformed, but it doesn't get to the point where you are exposed as a driver or passenger. So the idea here is to study the concept of the coefficient of restitution. So I am going to show you that. What I'm going to do is, perhaps it's a good idea if we just draw a simple object here, just one like that. That would be a ball of some material. And you can see we draw the ground over here, yeah? And we, of course, if we don't do anything here, you click on run, you say, oh my gosh, this should fall. But it didn't. Remember, we had set up the gravity not to act. So we need to put it back. This vertical gravity here. Run, both of them fall at the same time. Not a good idea. So we are going to fix this one, and this is going to fall on it. But you see, this is what you would normally you would expect to see. See? Okay, so if we go to, it's one thing to show this, but engineers don't. We're not good at pictures and these things. Pictures are nice, but they don't tell us things, and we want to be told what the forces are, what the velocity is, where is it. That's what engineers do. So in here, I am going to go in here and I say define for me. I'm going to say the vector. I'm going to ask for the velocity vector first. And I'm going to say, look, I also would like you to measure for me the position in the y direction. Okay? So there we go. I'm just going to go and then it's going to say, maybe like that. And you say run. And watch what happens. We in fact see how it bounces back and finally dies off. Now this is what we need. We want to see the position, we want to see the velocity, we want to see the forces that are developing here. That's why we do this. As you can see, we have a different emphasis than E110, because in E110, we are barely understanding what velocity and acceleration are. You guys are beyond that. We want to look at these variables and make sense for the purposes that we are set out to do. So we are going to reset. If I run, this, so you can see at the same time, I ask you to concentrate on this one, but I'm going to ask you to concentrate on this right now. Watch the center of mass of this. Do you see that vector? It's actually the velocity of this. See how the velocity goes up and down and up and down? Just like it's in here, but this is a vector in here. The interesting thing is that in working model 2D, we could actually, it is so good that we could actually play our thing in real life. If we want to look at every millisecond, we can. And that's exactly what we need to do to protect people in cars. Because, just to give you an idea from the very beginning, a crash occurs in less than 150 milliseconds. So that means less than two tenths of a second. Everything is done. So with tools like this and us being able to analyze what happens every fraction of a second, that's exactly what we need to be able to get closer to understand what happens in a real situation. Okay, so in here, you see, we can go every step. We change the step of integration, but you see how the velocity change? And the ball goes up and diminishes, the velocity goes to 0. And then it's going to go down again. And then it's going to bounce again. And then it's going to go up again. Until down, until no more. Yeah.
You essentially do that for the bottom block. So let's say it's like, I guess in reference to that, if someone hits like a parked car.
Yeah.
you can say what was the impact on the other car, I guess how far it moved, or if it moved, and then moved back to its original position.
What happens is that in here, look at the to answer your question more precisely, let's take a look at these numbers here. Do you see this number? With zero point 0.5, you expect that there will be some bouncing back. Okay? That's not what happened if you hit a parked car. They will not going to be like this.
Yeah.
It will go boom, but there's no restitution, or there's little restitution when they separate, but they don't come back again. So the restitution in vehicles is less than zero point 0.5. In fact, to give you now the voice of experience is about zero point 0.1. So that's what we would expect to see in real life vehicles. Um, some restitution, but small because they deform. You hit a parked car and you cause damage to your car on the other, but there's the no bouncing back like this. I am doing this deliberately to try to get to you the concept. Okay, now that you raised that question and I told you about the number, what would happen if on this ball I set this number to 0? Hmm? What do you think will happen? Coefficient of restitution is 0. Hmm? Huh? What do you think will happen? It won't bounce? All right. Let's see. Hmm? Right. We did good. Proving exactly what we are saying the real life is. For example, if you show this to a jury and you show it to a judge that never took E110, it's going to be clear, right? Look, there's no, if we set this number to 0, it's totally plastic collision. And what happens is when you have two bodies, the collision is going to be controlled by the body that has the least coefficient of restitution. Because remember, the other one is still set at 0 0.5, see there? But this one is set at 0. So that's going to be the result. No bouncing. But now we are going to take and do the, obviously here you can see also no bouncing. But I am going to set this to 1. And what would you expect will happen now? Let's see those good brains. What if we set this to 1, what will happen? And also, what's the meaning of this? 1 means totally elastic collision, right? Okay, so what would you expect will happen? It will bouncing forever. Okay, let's see if it's true. Uh-huh. Something went wrong. What went wrong here? Huh? The ground now is lower than the body itself. So what's happening now? The body itself is not deforming, but the ground is. So now to simulate a totally elastic collision, we need to set this also to 1. And now what? You see what I mean? Isn't this a lot of fun? We understand a concept that is hard to, we didn't do the equations of momentum and all that stuff, which we should. And I promise I will do it in the next lectures. to a little bit to study a little bit more about the coefficient of restitution. But my point is that by proving the with the computer simulation and putting the values, the correct values, we understand the physics of this. That's the point of this whole thing. And this is a concept that is very important because cars will never be like this. Can you imagine two vehicles that are like this would be deadly to anybody? Can you think why? Why? Huh?
Too much impact acceleration.
No. It has to do with the what we were talking about, the dissipation of energy and the deformation. This means no deformation, right? So it's like going just put two people inside two billiard balls. That's exactly the situation, very similar to this. Billiard balls don't deform. So, and because they don't deform, energy and momentum are conserved. They're not dissipated. You want in a let's just talk about other fun things because it's interesting. In this class, we can mix all kinds of other things that we learned in the past. Remember the in E110 we talk about the principle of impulse momentum, right? The conservation momentum, and Beer and Johnson book has an example of a batter hitting a baseball. So the pitcher throws the ball at you, and you swing. You're swinging the other way, right? And the objective and the whole game is to change the momentum of the ball, but changing the momentum in the opposite direction as it's coming in. Okay? Let's just think about as it relate to what we just said. What is it better? That the baseball, in this case, deforms completely or that it doesn't deform? Huh? How do you do home runs? If the ball doesn't deform, right? Because the momentum that the pitcher throws the ball at you, plus the swinging momentum that you give it, these two things are going to, the change of momentum is going to be the sum of these two. And when you get like you want a big change of momentum, so you do a home run. What about pitcher throw the ball at you and the ball disintegrates on your bat? It's not going to go anywhere. Do you see my point? So in that, you want close to elastic collision. In the vehicles, we want close to plastic collision. In the vehicles, we want to dissipate energy. In the baseball, we want to conserve energy. And if at all possible, give it the whole energy of those big arms of the batter to make the home run. Let's think about the ball too. The baseball is not like a billiard ball either, right? But it's close, it's hard, it's very stiff ball. And it has all those seams that by now, those of you who are fans of baseball understand that you could rotate the ball and give it, you know, different kinds of balls so that the batter is fooled into thinking it's coming up when it goes down and things like that. That's part of the game. But the ball is designed pretty close to being a, for an elastic collision. But think about the bat also. If you swing with an aluminum bat, those of you who have played baseball, what happens? As opposed to a wooden bat, it goes farther, right? It really is easier to make a home run with a stiffer bat. But in professional baseball they use wooden bat. But the wood bat, you have seen them on TV. Those things bend, right? Sometimes they break. But the fact is that it is designed in such a way that it's not totally elastic collision either. I don't think it'll be a lot of fun if it would be totally elastic collision. Because everybody will make a home run, just like we did over here. Forever bounce, it's like magic. But no, it's based on this very basic important principle of the coefficient of restitution. I want to close this video of this principle by making a little summary of what I said. In the simulation that we have in here, the coefficient of restitution is 1. Totally elastic collision, meaning the ball goes back to where it started and it will go on forever and ever and ever. In fact, I'm gonna let it go past the scale. The computer resets the scale and it keeps going forever and ever. Yeah? If we do the opposite, one of the bodies has a coefficient of restitution of 0. Now we have a whole different thing. The body goes, no bouncing at all. So, conclusion of what I have just said is that the coefficient of restitution controls the collision between two bodies. And that's the message I want to give you, that we have to have a control of these numbers to be able to represent real life situations, like when we have vehicle collisions. This number is going to control a lot of what happens. But I already told you they're close to 0.1 restitution, which is basically telling you that 10% of energy is restored, 90% of energy is gone, which is the way deliberately cars are designed. So I will save this as our first introductory video for the concept of the coefficient of restitution.